Hi. The next topic in Chapter 6 is plastic deformation. Now, of course, this is defined as the permanent deformation of the material. In other words, you stretch the material out, and then atoms move around, there's slippage in the planes, and things don't go back to the way they were before when you release the load. There's a few things that we want to define here. First of all, today I'm going to be talking about this plastic or permanent deformation at lower temperatures. If you increase the temperature of the material, of course, it's easier lots of times to get it to plastically deformed. So what we're going to be talking about is sort of room temperatures or temperatures that are, say, a third, less than a third of the melting temperature of the material. So I'm again still discussing what happens when you're doing a simple tensile strength test where you're taking the material and you're pulling on it like this. And in that case, we're going to define the plastic deformation as watching this stress-strain curve in a tensile stress test. Okay? So what happens is you pull on it, and then you've got the elastic regime that we talked about in the last lecture. But then once you exceed sort of the stress that can be returned to normal after you release the load and it begins to plastically deform, if you release the stress, then you'll have some permanent deformation of the material and you'll have a plastic strain, sometimes defined with epsilon sub p there. Okay, so you have a plastic strain. All right? Now, there's a number of different parameters that engineers have defined over the years to sort of define how well a material responds to stress or to quantify those things. So you're going to learn a little bit of new vocabulary today. The first bit of new vocabulary that you're going to learn is called the yield strength, often symbolized with sigma y. This is defined as the stress at which noticeable plastic deformation occurs. So since noticeable is kind of subjective, what they've done is they've put a limit on it. And what they're saying is that noticeable deformation occurs when the plastic strain is 0.002. Okay, so that's basically a 0.2% change right in the length. Okay, so what you do to find the yield strength is you have your curve, right? And then you do a fit to the elastic or linear region, okay? And then you construct a parallel line that intersects your strain axis at 0.002, and then you go back to where your straight line constructed fit intersects your stress strain curve, and that will give you your yield strength. So that's all there is to it, okay? If you compare the yield strengths for different materials, then it's really hard to measure that for ceramics because they just break, right? As we discussed last time, you put a ceramic material under a stress and it'll fracture once it gets past that elastic regime, and so you just can't measure it at all. But yield strengths for metals and alloys can range into the gigapascal range up here for steel, and then all the way down to very low values for something like tin. Interestingly, there's overlap in the yield strengths between some of the stronger polymers and some of the weaker metals. And so, of course, the yield strength for polymers is much lower than most metals, but there you have it. And then, of course, for composites, you're often going to mix your metal alloy with, say, a ceramic or something like that, in which case a lot of them break, just like the ceramics break. So it's kind of difficult to measure for that. The next new bit of vocabulary you're going to learn is the tensile strength, sometimes abbreviated TS. The tensile strength is defined as the maximum stress on an engineering stress-strain curve. So first of all, let's talk about what a full stress-strain test looks like and what the resulting curve looks like. What you've got here is you've got a material that you're pulling on in one of those tensile testing machines, and then you measure the resulting strain, and then you plot that stress versus the strain. So you start off and you're in the elastic regime and it's got kind of a linear trend. Then you begin to plastically deform the material. Now up here near the maximum of this curve, something happens. A neck begins to form. In other words, the material starts to thin out noticeably in one region of your sample, okay? And it forms this little neck. And then it continues forming that neck. The necking region gets longer and thinner until fracture occurs, and then basically the tensile test is stopped. So basically in a tensile test, you pull on something with increasing amounts of force until it breaks. And then you plot the resulting strain that comes out. And this is what they look like. They go up linearly, they come to a peak, and then they start going back down with the neck forms until fracture occurs. Now, in metals, this maximum stress is when the noticeable necking starts. In polymers, it occurs when those polymer backbone chains are aligned and they're about to break. So if you compare the tensile strength of various materials, you can, of course, measure for ceramics where the maximum on your stress strain curve occurs, all right? It's usually going to be right before it breaks. Oftentimes, though, I have to tell you, you don't usually stick ceramics, glasses, things like that in a tensile testing machine. It's just not safe. What happens is you pull and pull and pull, and then it shatters, and then shards of glass and ceramic fly everywhere. So usually when you test the tensile strength of ceramics, you do it in a different way and not in a tensile testing machine. But you can see that the maximum values for the tensile strength for metals and ceramics are kind of comparable up here. And of course, it's much lower than polymers. And unsurprisingly, composites span the range between metals and polymers. Ductility. Another new vocabulary word. Ductility is defined as the plastic tensile strain at failure, or the percent elongation of the material. All right? So the percent elongation is the change in length from fracture point, the length right before fracture, to the initial length divided by the initial length and then times 100%. So that's ductility. You can see here that they're sort of backing it out and doing the fit and extrapolating, but remember that yield strength, they're comparing the yield value here to get the plastic, but oftentimes that yield is not a very high number. It's like 0.002, and so you can usually ignore that for the test that we'll do in class. Okay, another way to measure the ductility is to calculate the percent reduction in area. We talked about how if you have a lengthening in one direction, then of course you have a constriction in that lateral direction. So as the length gets larger, the cross-sectional area gets smaller and smaller. So if you want to compare it that way, then you can compare the initial area to the final area, subtract those two, and then divide by the initial area and multiply by 100%, and you have percent reduction in area. That's another way to calculate ductility. Brittle materials usually fracture at less than 5%, so they don't change their length or their area very much at all before fracture. Toughness is the energy that is required to break a unit volume of a material, or the ability of a material to absorb that energy and plastically deform before fracturing. And you can calculate this by calculating the area under your stress-strain curve. Remember, we're sort of likening stress-strain curves to force versus displacement curves for springs. And if you integrate a force versus a displacement curve, you get work or energy. So it's the same kind of deal. So an energy would be the area under that stress strain curve. So if you want to calculate your toughness, you just calculate the area under your curve. The resilience is the ability of a material to store energy and then recover energy after the release. So this is when you calculate the area under the curve, but only in the elastic region, okay? Now, since the elastic region is usually that straight line bit, then the area under the curve is a triangle, okay? And so you can approximate the resilience as 1/2 the the yield strength times the plastic strain at that point. Okay, let's do an example problem. And this example problem will really help you get through the lab that we're going to do on tensile testing, because this is how you'll analyze your data. This is from your textbook. A cylindrical specimen of aluminum having a diameter of 12.8 millimeters and a length of 50.8 millimeters is then pulled under tension in a tensile testing machine. So use the load elongation characteristics shown in the table. They give you a table of values to answer the following information. Plot the data as a stress strain curve, compute the elastic modulus, determine the yield strength at a strain offset of 0.002, determine the tensile strength, find the approximate ductility and percent elongation, and compute the modulus of the resistance. Now, in the problem, what they gave you was the load versus the length. And this is usually what's outputted by a tensile testing machine. And then from the load, you can calculate the stress by comparing it to dividing the load by the cross-sectional area. And you can calculate the strain by dividing the length, the change in length divided by the initial length. Okay? So here, if you start out at a load of 0, the initial length of the material was 50.8 millimeters in the data that I was given in the problem. And then here's the load. So I used this initial length and the information given for the diameter of 12.8 millimeters to calculate the stress. So I took this load column and divided it by pi r squared to calculate the stress here, which is in the last column. And then for the strain, I took the final length, or I took the length at any given point and subtracted off the initial length and then divided by that initial length. Okay? So for example, for right here, 50.85, then the strain would have been calculated by 50.85 minus 50.8, which is 0.05, and then divided by 50.8. And that gave me the value in that column. And then I plotted the stress versus the strain here. Okay? I did this in Excel, and I got a stress strain plot that I plotted in Excel and put out here. Underneath the lecture, I give you the Excel file in which this data is outputted. Okay? So that's part A. It wanted the stress strain curve. Now in part B, it asked you to compute the elastic modulus. So what you do for that is you take the linear portion of your stress strain curve and you fit that using whatever routine you like to a straight line. So I just took the first 1, 2, 3, 4, 5, 6 data points. Okay, I took the first 6 data points, fit a line to those in the Excel, and got a straight line fit. And then from that straight line fit, I can use the slope, and the slope in the trend line will give me the elastic modulus. And I got 60 gigapascals for that elastic modulus. So that's how you do that part. Next it said, determine the yield strength at a strain offset of 0.002. Okay, so this is the point at which plastic deformation occurs. So basically, the strain offset line is going to have the same slope as the elastic portion of your curve, and then it's going to intersect that strain axis at whatever point it defined, here 0.002. So that means that your y-intercept for your line is going to be minus 60 gigapascals times 0.002. Okay, so that's B. And your slope is, of course, 60 gigapascals. So your equation for that straight line curve is going to be 60 gigapascals times the strain minus 60 gigapascals times 0.002, your y-intercept. And then what you do is you plot on the same plot the straight line curve that you got versus the stress strain curve, and you look at where that data intersects, and where the data intersects you read off your stress. And so that's what I did. I moused over that point on the line, and I got 0.276 gigapascals for my value. So that was my yield strength. Next, determine the tensile strength. So the tensile strength is really easy. All you have to do is read off the maximum at your stress strain curve. So the maximum of the stress strain curve occurs right around in here somewhere. And if you read off that maximum value, you get 369 megapascals. Done and done. Finally, what's the approximate ductility in percent elongation? Well, for ductility, what you do is you take your change in length, your total change in length, comparing the initial value to fracture, and then you divide by your initial length times 100%. So my final value in that chart that they gave me was 59.182 millimeters minus my initial, which was 50.8 millimeters, and then divided by my initial times 100%. When I did that, I got 16.5% for my percent elongation for the ductility. Then next, it asked compute the modulus of resistance, and the modulus of resistance was defined as 1/2 times my yield strength times my plastic strain at that yield strength. And so I got 0.0066 times 0.276 gigapascals divided by 2, which gave me 9.11 times 10 to the 5th joules per cubic meter. All right, so that's how to do it. Now, oftentimes we'll differentiate between the stress strain as plotted on an engineering stress strain curve in the blue here, like I've been talking about for a while, and we'll contrast that to the so-called true stress and true strain curve that's generated. And the idea here is that if you looked at this engineering curve in blue, it's got a downward trend at the end near fracture. Well, that downward curve might make you think that the material is actually losing strength, right? That it's not as able to withstand the stress. But that's just not true. What's actually happening is, remember that that neck is forming, and at that neck, your cross-sectional area is a lot smaller than it was at the beginning when it was a lot fatter. If you correct for that and instead divide by the true area as you stretch it out, then you can see that the red curve is what results, okay? And the red curve will show you that your material is actually increasing in strength as it's deformed. Now that may seem a little strange, but what's happening is that as you increase in strength, you're increasing the number of defects that you've got in the material. You're introducing all kinds of, slips and dislocations and voids, and these defects actually make the material stronger. Defects can make a material stronger, which is why people beat on materials and do all kinds of work hardening to make their materials stronger. And so that results in this true stress strain curve. Now the formula for true stress is going to be the force divided by the area at the ith data point. So wherever you are on that curve as you move across, you're going to divide by the actual area of the material at time ti. Okay, so sigma true is equal to the force divided by the true area. You can do a derivation that we'll show in a second and show that this is actually equivalent to the engineering stress times 1 plus epsilon. The true strain is defined as the natural log of the initial length divided by, the length at the ith time t is equal to ti divided by the initial length. And that's also equal to the natural log of 1 plus epsilon. So, prove it, right? Starting from the definition of true stress, the force divided by the true area at whatever time you're at, and the true strain, that the true strain is the natural log of Li over L naught. Prove that those formula that I showed on the previous slide, the sigma true is equal to sigma times 1 plus epsilon, and epsilon true is the natural log of 1 plus epsilon. Prove that it's true. Okay, so here's my proof. So I want to prove that this is true, that sigma true is equal to sigma times 1 plus epsilon. So I'm going to stick in the definition of epsilon first. So that's sigma times 1 plus Li minus L naught over L naught. Remember, L naught here is my initial length, and Li is the length at time t is equal to Ti, okay? So if I expand that fraction right there, Li minus L naught over L naught, then I get sigma times 1 plus Li over L naught minus 1, and that's because you're subtracting off minus L naught over L naught, which is minus 1. And then the 1's cancel out, and I end up with sigma times Li over L naught. Now, here's the assumption. I'm going to assume that volume is conserved. So I'm going to assume that the area here at time t is equal to Ti times the length at time t is equal to Ti is equal to the area at time t is equal to 0 times the length at time t is equal to 0. And then I'm going to plug that into my equation for sigma true, which is the force divided by the area, the true area, AI. And if I plug in for AI, then I get F Li over A naught L naught. And then that equals, since sigma is defined as F over A naught, that equals the engineering stress times Li over L naught. So what I've shown here is that this definition of sigma true and this definition of sigma true are equivalent. They end up with the same thing, so that proves that the definition of sigma true, sigma times 1 plus epsilon, works. Next, I have this definition of my true strain. Epsilon true is equal to the natural log of 1 plus epsilon. Okay? Reminding ourselves that epsilon is equal to the change in length over the initial length, And that then, therefore, if you shrink that down for a very small time increment so that the length hasn't changed much, you get d epsilon is equal to dl over L, right? So if I plug that in for my true strain here, epsilon true is equal to the integral of d epsilon, and I integrate that value, dl over L, then I get a natural log. And I get the natural log of the length at time t is equal to ti minus my natural log of the initial length, which then, of course, by the law of logarithms here, that's equal to the logarithm of the ratios of Li over L naught. Now, we've already shown that Li over L naught is equal to 1 plus epsilon. We did that on the previous slide. So if I plug that in, then I get epsilon true is equal to the natural log of Li over L naught, which is equal to the natural log of 1 plus epsilon. And I'm done. Okay? So it's not very difficult then to convert an engineering stress strain curve over to a true stress strain curve. And you'll do that for homework. So thank you. Let me know if you have any questions, and I hope you enjoyed it.